Okay, so let's continue, I guess, with the flow similarity. So one question that you want to answer is, how would our analysis, how would our studies, experiments, and whatnot in a detail would apply to the real world? And how would we make the measurement, force measurements, lift, drag, all of these different measurements, and then apply this analysis, apply this measurement to a real world aircraft, right? And that's where the flow similarity comes into play and all of the dimensionless parameters. The idea is we introduce these dimensionless parameters that we did talk about a little bit. We talked about the Reynolds number and the Mach number. And these dimensionless parameters are dimensionless by definition, meaning that dimensions of the aircraft, dimensions of your control volume, whatever that is not going to be important. So essentially, if you measure a dimensionless parameter for a scale model of your aircraft in a wind tunnel, you can, for the same conditions, for the same Reynolds number, whatever, you are going to have the same dimensionless parameter for a real aircraft that's flying at the same Mach number, for example. Does this make sense? So the idea of flow similarity and the introduction of dimensionless parameters. There are two dimensionless parameters that we already know, the Reynolds number and the Mach number. And let's actually talk about these dimensionless parameters. Other dimensionless parameters that are very important in aerodynamics specifically are force coefficients, like aerodynamic force coefficient, lift coefficient, drag coefficient, and normal force coefficient, actual force coefficient, moment coefficient, all of these things. How do we calculate any of these force coefficients? Okay, the goal is to come up with a parameter that is dimensionless and gives us an idea about the force that is being exerted on your body. So what we do is we take the force, for example, in the case of lift coefficient, we take the lift force, and then divide it by a dynamic pressure multiplied by the area. And if you recall from your fluid mechanics or aerodynamics, doesn't really matter, pressure multiplied by the area is always going to give us force, right? Let's see. Okay, where? This is our lift, and we are going to multiply the dynamic pressure by the area to calculate the force coefficient, the dimensionless coefficient, which is called the lift coefficient. What is dynamic pressure? It is the amount of kinetic energy in your air. And how do we calculate the kinetic energy in our air? Density multiplied by the velocity squared. This is called the dynamic pressure. And this definition applies to all of the other force coefficients as well. So the all of the other force coefficients as well. Drag coefficients, you calculate the drag coefficient, you divide your drag force by dynamic pressure multiplied by the area. And which area is this? This is the span area, essentially the area of the wing. Normal force coefficient, the same thing. You divide the normal force by the dynamic pressure multiplied by the span area. Actual force coefficient, exactly the same thing. There are a couple of things that are a bit different, like the moment coefficient. You have to include a moment arm as well, right? In your analysis, you have to divide the moment. Moment is force multiplied by an R, right? To find the dimensionless coefficient, we divide the moment by the dynamic pressure multiplied by your area. It's going to give you a representation of the kinetic force in your system multiplied by the arm. Do you have any questions? So flow similarity, essentially for a flow, for two different flows that have the same Reynolds number and the Mach number, have the same characteristics, If you measure the lift coefficient for one, you can say the other one also has the same lift coefficient, right? If you measure the drag coefficient for one, you can say the other one also has the drag coefficient. And if you have the geometric properties, meaning that if you know the flight velocity and all of the length and stuff, you can actually find the total drag force that is being exerted on a real plane using a wind tunnel analysis. Does this make sense? Okay. So again, yes.
Are there any parameters other than the Reynolds number and Mach number that contribute to this?
It can be any dimensionless parameter. It doesn't have to be Reynolds number and Mach number. But the thing is, we say that when two of these parameters are the same, the other dimensionless parameters have to be the same as well. Right? So the two different flows are similar if at least two dimensionless parameters are the same. And the flows are geometrically similar. You cannot do this test for a sphere in a wind tunnel and then apply it to a Boeing in the real world. It has to be a scale model of a Boeing and a real Boeing. Okay. Let's solve an example problem. This example problem will make everything a little more clear what flow similarity is and how to solve problems for it. So we have these two different flows. Both of them are flows over spheres, right? And at one condition, we have flow with V1, rho 1, and T1 for velocity, density, and temperature, flowing over this sphere with a diameter D1 and a surface area S1 goes into the plane. And then the next flow that we have, which is geometrically similar, both of them are flows over spheres, has twice the velocity, 1/4 of density, 4 times the temperature, essentially, right? And 4 times the diameter. So these two flows are geometrically similar, but their conditions are different: velocity, density, temperature, and also the diameter. And we want to see whether these two flows are similar, dynamically similar. So what do we need to do? The idea was, the definition of a dynamically similar flow was that these two flows are or have let me use this. The two flows have to have at least, they have to be geometrically similar. And two of the dimensionless parameters have to be equal. I mean, one has to be equal, but we can investigate the other. What were the flows? We have flow over a sphere, V1, rho 1, T1, and diameter 1 in area S1. And the next flow is, again, flow over a different sphere, 4 times V1, right? V2 is 2 times V1. I don't remember the density and velocity and everything else. Was it divided by 4? Divided by 4, and temperature is 4 times as well. So rho 2 is rho 1 divided by 4, and T2 is T1 by 4. 4 multiplied by 4. We want to investigate whether these two flows are dynamically similar. So the first condition is already met. These two are geometrically similar. The second condition, we have to calculate one of the dimensionless parameters. What are the dimensionless parameters we have seen so far? Reynolds number, which we talked about in the previous lecture, and also the Mach number, and all of the force coefficients, lift coefficient, drag coefficient, and whatnot. Okay. Let's focus on these two. Reynolds number. How do we calculate the Reynolds number for this specific problem? How do we calculate the Reynolds number? What is the equation for Reynolds number? Rho V L. In this case, we have a sphere, right? So we have to use the diameter of the sphere. If it was a flow over a flat plate, you would have used the length of the plate, right? So rho VD divided by mu. What is the Reynolds number for case 1? So rho 1, V1, D1, or let's use the small letter d, divided by mu 1, Reynolds number of 1. What about the Reynolds number of 2? Rho 2, V2, D2 divided by mu 2. Okay? We know the relationship between rho 2, V2, D2 and rho 1, V1, D1. Let's just substitute rho 2, V2 and D2 for their, I guess, the one counterparts. Which means that the Reynolds number is going to be, at 2 is going to be rho 1 divided by 4 multiplied by 2 V2 multiplied by 4D, is it 4 or 2? 4D1, right? Divided by mu 2. What is the relationship between mu 1 and mu 2? Do they have any relation?
Well, they have the same kinematic viscosity, so the same, but density is different, so the dynamic viscosity would be different.
We are not told the flows are the same. So we don't really know if the dynamic viscosity is the same. Yeah.
Didn't we say that mu was a function of pressure and temperature?
Yes, exactly. So in the previous lecture, we specifically talked about the dependence of viscosity on temperature, right? And we did talk about the Sutherland's law, right? And we said it is an empirical equation that relates the temperature to the viscosity. And we can show that the viscosity is related to the square root of temperature. Okay? Which essentially means that the viscosity of at 2 is related to the square root of temperature at 2. I'm sorry, 2. And then I'm going to substitute this for T1 multiplied by 4. So viscosity at 2 is related to 2 times the square root of T1. The square root of 4, T1. So 2 times the square root of T1. Okay? What is the square root of T1 related to? Mu1, right? Viscosity. Which essentially means that both of these have a relationship with the square root of T1. One of them is twice the square root of T1, which essentially tells us that mu2 is itself twice the square root of twice mu1, right? Does this make sense? Okay. So I'm going to use 2 mu1 here, and all of these, this is 2v1. All of these cancel out, which means that RE2 is going to be equal to rho 1 v1 mu1. I'm sorry, v1 mu1, which is equals to RA1. So we have proven that the Reynolds number of the second flow is equal to the Reynolds number of the first flow. Since they are geometrically similar and the Reynolds number numbers are the same, we can just say the flows are dynamically similar. Did they answer the question? We can do the same analysis for the Mach number. It will be somewhat easier with the Mach number because we only have two variables there. Just have to be mindful of the fact that the speed of sound is calculated with this equation, the square root of gamma RC. And this is an equation we did talk about in the previous lecture. Okay, so for this flow, we have proven that these two are dynamically similar. Let's say this is a smaller cylinder. Let's say we can put this in our wind tunnel. If you put this in our wind tunnel, calculate the drag force, measure the drag force essentially. Using the drag force and the flow velocity, you can calculate the drag coefficient, and then say for this exact flow for the second condition, the drag coefficient is going to be exactly the same, and then back calculate the drag force for the second flow. That's the ideal flow scenario.
So what is the S1 and S2?
They're just the surface areas of the cylinders. This is a cylindrical flow, so we have a cylinder, lower cylinder. Okay? Which you should use the S1 and S2 if you want to calculate the lift coefficient and drag coefficient, right? Because we had the lift divided by the dynamic pressure multiplied by the area, right? Any questions? No? Let's move on. So I'm going to give you a couple of minutes to solve this yourself. We have a jet that is flying in real life. They have the flight velocity is 250 meters per second. We are flying at 10 kilometers altitude with a density of 0.414 kilograms per cubic meter, temperature of 223 kelvins. And then we are testing a 1/5 scale model in the wind tunnel of the exact same jet. We are given the pressure in the test section, which is 1 atmospheres. And we want to calculate the temperature, velocity, and density of the airflow inside the wind tunnel so that the CD and CL are the same for these two scenarios, real flight condition and the wind tunnel flight. Essentially, the first thing you want to do is to calculate the Reynolds number for the wind tunnel case that is exactly the same as the Reynolds number for the Mach number for the real flight case. So let's see. I'm going to give you like 7 minutes. Whoever gives me a good answer, correct answer, will get a bonus point. Bonus one. Do we know how to start the problem? Have to set the two Reynolds number and the Mach number is equal to each other. What is the equation for the Reynolds number? Again, for this case. Rho VL over mu. What about the Mach number? It can also be rho v d over mu. Doesn't really matter for this problem, specific problem. Mach number is v divided by a. While you're working on this, I'm just gonna give you a paper to do one of the random attendance quizzes, I guess. Think of just write your name on attendance sheets. So instead of doing an attendance quiz, you're gonna work on this and then write your name on a piece of paper. Okay, do we have any questions? And for these things that I assign in class, you can work with your peers. You don't have to work on this. This is not an exam. And whoever gives me a correct answer will get a bonus point. The purpose is for you to start thinking and working on these things, right? So you don't have to work on this alone. You can work with your peers and friends. You don't want to? No, slightly here. With that lollipop.
How many points do we have?
What is it?
How many points does it have?
10.
Really?
But you only have 1 minute to give me the correct answer.
270.3.
Oh, you have printed the lecture notes? Yeah, it doesn't work that way. Got it? Okay, let's think about how to solve this problem. Okay? While the attendance sheet is being passed around, let's think about how to solve this problem. Let me Okay, so we have a real flight condition and a wind tunnel case. Reynolds number is rho v1L or d1, doesn't really matter, divided by mu. Reynolds number of 2 is rho 2 v2 L2 divided by mu 2. We don't really have anything for the wind tunnel case, the case inside the wind tunnel. But we do have the density and velocity and temperature of the real world scenario. But just based on knowing these temperature, density, and velocity, we won't be able to calculate a Reynolds number. So what should we do? We can just take the ratio of the two Reynolds numbers, right? And set it equal to 1. That's the idea. Let's see what happens if we do that. We're going to have rho 1 divided by rho 2, right? V1 divided by V2, L1 divided by L2, and mu2 divided by mu1. Does it make sense? Okay. For these two flows to be dynamically similar, the Reynolds numbers have to be equal. So this side of the equation has to become 1. Has to become 1. We do have the value of, bless you, we do have the value of density. What was the value of density? 0.4? 1.4. And we also have the value of velocity, which was 250, right? What can you say about these length scales? We don't really have any value for length, right? So how can we simplify this? How can we get rid of these length scales? It's a 1/5 scale, so any length is a 1/5 scale. So essentially, L1 divided by L2 is going to be equal to 5, right? And then what about the density? The density is a function of a square root of temperature, right? When you take the ratio of these two, you can just replace this with the square root of the temperature ratio. Okay? And what was the temperature T1? 223. Is that 223 kelvins? Or? Okay. Okay, so we have one equation that has T2, rho 2, and V2. Okay. Can we do the same thing for the Mach number? Okay. How do we do this for the Mach number? Let's take the ratio for the Mach number. Mach number 1, Mach number 2 is V1 divided by V2, A2 divided by A1. We have the velocity 1, but we don't have any information about the speed of sound. How do we calculate the speed of sound? What is the equation for the speed of sound? A square root of gamma RT. Yeah, exactly. So let's replace that with the square root of gamma RT T2, square root of gamma RT1. Gamma and R are the same thing because we are flying in air, and it is a wind tunnel that has air as its operating thing. So we can rewrite this as V1 divided by V2, the square root of T2 divided by T1. And again, Mach numbers have to be equal for this to be dynamically similar. So we're going to have 1 equals to 250 divided by V2 multiplied by the square root of T2 divided by what was it? 223. Okay. So what do we have so far? We have two equations. This is the second equation. This is the first equation. Can we find our unknowns using these two equations? No, because we have three unknowns. Two equations and three unknowns, right? The second density, rho 2, V2, and T2 are both unknowns. So we can't really use these to find unknowns. So what should we do? What is the other equation we can include here?
Pressure equals rho over RT.
The ideal gas law, right? So we can use the ideal gas law to see if we can find the third equation. What is the ideal gas law? Pressure at any point is equal to density multiplied by the specific gas constant multiplied by the temperature. We are operating in air, so we already know what the value of R is. What is the value of R? 287. Thank you. So we can write this for the wind tunnel case. P2 is equal to rho 2 R T2. What is the value of P? 1 atmospheres, right? And the units here has to be in Pascal, so 1.1 times 10 to the power 5 equals to rho 2 multiplied by 287 multiplied by T2. So this is your third equation. We have 3 unknowns, 3 equations. Which means that we can find the 3 unknowns. What are the 3 unknowns? You have the lecture notes printed out, right?
Yeah. Velocity, temperature, and density.
No, what is the value of it?
Value. So temperature is 169.67.
So T2 has to be 169.67 kelvins.
Yeah, the velocity is 217.3.
217.3 meters per second.
Yeah, the density is 2.07.
2.074 kilograms per meters cubed. So for these 2 flows, the flight in the wind tunnel, the test flight in the wind tunnel, and the real flight condition, for these 2 to be dynamically similar, the wind tunnel has to have these conditions: the density and temperature, and the velocity have to be like this for these 2 flows to be dynamically similar. And then when this condition is met, whatever the drag coefficient you calculate for the wind tunnel case, you can use in the real world scenario, or lift coefficient or whatever, right? Okay, what is the importance of a drag force, the drag coefficient or lift coefficient calculation though? Why do we care about lift coefficient or drag coefficient?
Try to figure out where an aircraft can optimally operate at.
Essentially, that's the whole idea of aerodynamics, right? We want to understand and calculate and measure the lift and drag force, right? And we can't really go measure all of these forces during flight, so we have to either use a numerical method or a wind tunnel to do the calculations in a smaller scale, and then apply that smaller scale to a real world scenario, right? Okay, any questions? No? Let's move on. Very simple. Okay. So, I usually don't really cover dynamic dimension, Buckingham Pi theory. I don't really know if I should cover it for this class or not. Who is familiar with Buckingham Pi theory? Not the aerospace one. When did they teach you this?
Last year, fluids.
Fluids? Who was your fluids teacher?
Dr. Wayne.
Oh yeah, excellent. Yeah. Okay, so I guess let's not do this one. Let's move to the chapter 2. Okay. Yeah. It's just we'll add to the complexity of the problem. Yeah. Let's just move on to chapter 2, and we'll go from here. So, chapter 1 was just mostly introduction, a little bit of basics, very simple cases of these dimensions, parameters, or dimensions, parameters, familiarities, and the relationship between aerodynamic forces. But in chapter 2, we are going to dig deeper in fluid mechanics review. We will talk about the governing equations behind fluid flow, which I'm sure most of you are very enthusiastic about, all of the partial differential equations. And then we will talk about inviscid flow, fluid kinematics a little bit, and we'll move on from there. Do we have any questions about the materials in chapter? So, Buckingham-Pi theorem, don't worry about it in the lecture notes. Just move on from it. We're just going to do chapter 2. Any questions, any concerns so far? Okay. Review of mathematics, governing equations, and everything else. We are going to start with a very, very basic review of vector algebra, though. Because in my experience, when you get to this point in your education, you either don't remember vector algebra, or you have never learned it for some reason. So it's not a bad idea to do a very, very basic review. What is a vector? First of all,
A quantity that has both direction and magnitude.
thank you. A quantity that has both direction and magnitude. So when we are talking about a vector, we are talking about something that has a magnitude and has a direction, like velocity, right? But temperature is not a vector; doesn't really have a direction. And we can have the basic mathematical operations on a vector. We can add vectors. We can subtract the two vectors. But the vector multiplication is a little different from a scalar multiplication. We have two different types of multiplications when it comes to vectors. We have the inner product and the dot product and the cross product. Okay, when you take the dot product of the two vectors, where you essentially multiply two vectors using the dot product operation, you are going to get a scalar, right? The final result of the dot product is a scalar, right? And how do we do the dot product? Take the magnitude of one vector multiplied by the magnitude of another one, multiplied by the cosine of the angle between the two. And cross product on the other hand is going to give you a vector. What can you say about the vector? What is the direction of the resultant vector of a cross product? It is perpendicular to the two vectors, or orthogonal to the two vectors. So if two vectors are in this direction, and you take the cross product, the other vector, the resultant vector, is going to be in this direction, that is perpendicular to the two. If you don't remember any of this, just stop me and ask questions. We have three different coordinate systems that we are going to deal with. We have the Cartesian coordinate system, cylindrical coordinate system, and a spherical coordinate systems. In Cartesian coordinate system, we have three axes, x, y, and z, and you can present each vector in the Cartesian coordinate system with its components, projections of that vector on each axis. In a cylindrical coordinate system, our axes are r, theta, and z. So essentially, like what happens in a cylinder, your radius, theta, which is your angle, and your height, z. In a spherical coordinate system, we are dealing with a sphere. So r, r, phi, and theta. So this is going to be your r. This is going to be your theta, and this is going to be your phi. We usually use the Cartesian coordinate system in our analysis, but there will be cases in which you have to use the cylindrical coordinate system. It's a two-dimensional cylindrical coordinate system, so you have to be comfortable with this. And we're going to solve ample example problems to make sure that you are comfortable. So we have two different types of fields. We have scalar fields and vector fields. A scalar field like pressure, density, and temperature. Whenever we say a scalar field, we are essentially referring to the fact that pressure or density or temperature can be different at any point in a field. Like in this room, temperature, it's very hot all over the room, but the temperature here is going to be different from the back of the class. The same is true for the vector fields, right? The difference is in just the fact that the vector fields have a magnitude, all of them. And in each direction, we can have a field for that vector field. What does that mean? So for a velocity vector, we can find the velocity in each direction, in in the x and y and z direction. The velocity in the x direction or y direction, z direction itself can be a function of x, y, and z, which essentially means that the velocity in the x direction here can be different from over there at the end of the class. Any questions? We have the procedure of dot product and cross product here. So whenever you forget how to take it, I'm sure you won't forget how to take the dot product, but if you forgot how to take the cross product, you can come here and use these equations that we have for the different coordinate systems to take the cross product of the two vectors. Okay. But the most important mathematical operations for us is the gradient, the curl, and the divergence. All of these operations are done by multiplying an operator called the del operator by your parameter. If you multiply your del operator by a scalar field, you're taking the gradient of that scalar. What is the del operator? This is the del operator, or the nabla operator. Essentially partial x. This is actually the del operator itself is a vector. Just to make sure that we are clear on this. Del operator is the gradient of your field, whatever that is, in the x direction, and this is in Cartesian coordinate systems. The gradient of your field, whatever that is, in the y direction, and the gradient of your field in the z direction, or the derivative of your field in the z direction. When you multiply this by a scalar like pressure, we call this taking the gradient of pressure. Your final result is going to be like this: partial p partial xi, partial p partial yj, and partial p partial zk. Okay. So we have a scalar field. We took the gradient. We essentially applied the del operator. What will happen to your scalar field? What is it? It will become a vector, right? That's a very important conclusion. Don't make it. Yeah, I've seen a lot of you make mistake here. When taking the gradient of a scalar field, the result is going to be a vector. And it does make sense. So when you're taking the gradient of any field, you are investigating the amount of change in each direction. And the change of pressure can be directional, meaning the change of pressure in x can be different from the change of pressure in y, right? And z. So it makes sense that the gradient of a scalar field is a vector, right? Because the amount of change can be different in each direction. Do you have any questions so far? Do we remember this, the gradient? Okay. And then we have the gradient formulas, again, for pressure in cylindrical and spherical coordinate systems. You don't really have to memorize this. You can bring this with you on an exam or any problem. But then what happens when you apply this del operator to a vector field, or you multiply it by a vector field? In a vector field, we have two types of, for two different vectors, we have two different types of multiplications. One was the dot product, and the other one was the cross product. So for velocity, we can have del dot v or del cross v. This operation is called divergence, taking the divergence of velocity. And this operation is called curl. Okay? So let's just for practice, let's do this. We said that del operator is this vector, again in Cartesian coordinate systems. we are taking the dot product of this and the velocity vector. Vxi, Vyj, and Vzk, Cartesian coordinate system, or UVW, same thing. What is the result of this operation? What is it? Yeah, just tell me what it is mathematically. Let's take the dot product. Let me use a different color. How do we do dot product? You multiply each component with each other, right? And then you get rid of the unit vectors, I, j, and k, right? Okay. So what is it? What is it?
Oh, partial
Vx, partial x, plus partial Vy, partial y, plus Vz, partial z. So, what does it mean? When you take the divergence of a vector, you are going to end up with a scalar. And what does this scalar represent? What do you think? Magnitude of what? We are taking the del operator. Whenever you apply the del operator, you are measuring some sort of a change because you're taking a gradient, right? So this is a magnitude change of something. But change of what? When you take the divergence. When we took a gradient, we measure the amounts of change in each direction for a scalar, right? What happens when you take the divergence of a vector, divergence of velocity here, for example?
The change in direction.
No, it is a scalar, so it doesn't give us any understanding of direction, right? Collective change. What is it? What does that mean, the resultant change? So let's think about it this way. Let's say I have a, let's use a combustion example. Let's say you have a droplet, fuel droplet, and you combust it, right? What is going to happen to that droplet? A big fuel droplet, right? It is going to shrink, right? Its volume is changing, right? Taking the divergence of velocity specifically is going to tell you the rate of change of volume of that liquid droplet, of that fuel droplet, while it's shrinking. Does it make sense? Okay. And we're going to see later on, for an incompressible flow field, which volume should not change at all, this has always to be is always equal to 0, right? So the divergence, taking the divergence of a vector, is going to tell you how much of a volumetric change you're going to see in that vector field. How much shrinkage, or essentially it's a representation of diffusion in your system, right? How fast or slow something diffuses in your system. Okay? Right? Yes?
So if it's in 2 dimensions, it's the change of area.
That's the idea. Okay. So we have the divergence in all 3 different coordinate systems. Let's move on to the curl of velocity, or curl of a vector. So, as we said, we have 2 different types of multiplications. Then you're dealing with 2 vectors, and you're multiplying 2 vectors. We did talk about the divergence of a vector, when you take the cross product of the del operator with a vector field, you are taking the care of that vector. And how do we take the care of? I'm not going to write it on the board, but essentially you just have to take the determinant of this matrix. All the equations are listed here. But what does taking the care of velocity specifically tell us?
It tells you the change in velocity in respective directions. The direction.
Changing velocity in each directions. It is going to give us a vector, so I can see where you're coming from. But this is true. So this is a vector is actually correct. That when you take the curl of velocity, you are measuring the amounts of change of velocity in each direction. But one thing you have to keep in mind here is that the velocity is a vector, right? And in each direction, when you take a curl, the direction also can change. That's just a magnitude. So it can get a little confusing, but if you bear with me, you're gonna see what it means. So when you're taking the curl of velocity, you are also measuring the amount of change in direction in each direction, right? Let's look at this specific problem. This is my velocity, right? If I take the curl of velocity, and the curl of velocity is going to give me a vector field that is normal to this, comes out of the board, right? That's the idea. If this is a non-zero thing, this essentially means that my velocity field, its magnitude can change to this, but its direction can also change, right? And like this, and like this. What does this mean? It means that we can have circulation in our system, right? So the direction of velocity is also changing. So you're going to have a vorticity in the system. You can have a circular flow. Does this make sense? A non-zero curl. Mathematical operations. So curl, gradient, and divergence are very important for aerodynamics. You have to become comfortable with them. Let's move on. Let's talk about, we have talked about the derivatives so far. Let's talk about the integrals. So the only thing that we are concerned with is these integral relationships, the Stokes theorem, the divergence theorem, and the gradient theorem. And we're going to use them later on to, I guess, simplify a couple of equations. Okay. What does the Stokes theorem do? The Stokes theorem converts a linear integral of a parameter to a double integral by just taking the curl of that parameter inside. The divergence theorem converts a double integral of a parameter to a triple integral by taking the divergence. And the gradient theorem converts a double integral of a scalar to a triple integral by taking the gradient of that parameter. Again, this is just a reminder of the mathematics. We are going to use these later on, so hopefully you will become a little more comfortable with the Stokes theorem, all of these theories, and the gradient, divergence, and curl. Any questions so far? It's either a lot of questions or no questions, right?
So can I consider the curl as the rotating axis?
That's the idea, yeah. Okay, so let's talk about the governing equations in a fluid flow. And those of you who have had another class with me, propulsion or I don't know, fluid mechanics. We don't have anyone in this class who has had fluid mechanics with me, right? No. We have gone over the governing equations in a fluid flow many, many times. So my expectation for those of you who have been in a class with me is to know all of this, right? And to answer my questions. Right? Let's see how it goes. So, governing equations. There are three principles that govern the movement of fluid anywhere. First is conservation of mass. Second one is the momentum equation. Or let's start with the second Newton's law. And the energy equation, or the first law of thermodynamics, right? We are going to start from the second Newton's law and first law of thermodynamics to get to more complicated equations that apply to fluid flow. Let's start with the conservation of mass. What does conservation of mass mean?
Full volume mass flowing in is mass flowing out.
That's the idea. Mass is neither created or destroyed. Divergence, we'll get there, right? Divergence of velocity is 0 for an incompressible flow fluid, though, right? Does that mean for a compressible flow fluid we don't have conservation of mass? Right? So that is not always the case. That's one point. But we are going to get there. So let's take a look at the fluid flow inside the duct. These are all walls. We have flow coming in, flow going out. There is no change with time. There's nothing happening. What is the conservation of mass? Mass flow in has to be equal to mass flow out. How do we calculate the mass flow in? That's the equation for the mass flow rate. So rho AV in is equal to rho AV out. Right? That's the idea of conservation of mass for a steady state scenario. But then we want to find the equation for a very small element in a fluid flow, not a huge duct, which essentially means that we want to find the integral form or the differential form of this equation. Okay? We did make a lot of assumptions here. We assume that the flow is a steady state. We assume that the flow inside is uniform, meaning that the flow at each point is moving with the same velocity and moving out with the same velocity at each point, right? That's why we could simplify the conservation of mass to this. But the idea of conservation of mass is pretty simple. Whatever mass goes in has to come out, right? There is no mass destroyed or created. That's the idea of conservation of mass. Let me actually write this down. Is neither created. What's the spell of the neither? N-E-I-T-H, yeah. Unbelievable. Neither created nor destroyed. There's no here. Okay. We're going to derive the conservation of mass from two different perspectives, the integral perspective and the partial differential perspective. Let's just start with the integral perspective. For the integral perspective, I'm going to introduce a theorem, which is called the Reynolds transport theorem. We are not going to prove that theorem, just have to, I guess, accept it. Reynolds transport theorem. I think those of you who have had the fluid mechanics with Dr. Link have seen this Reynolds transport theorem. I'm not sure if you have had if you have seen this if you have had the fluid mechanics with Cyrus. But I'm sure if you have seen it if you have had this with Dr. Link. Okay, what does the Reynolds transport theorem tell us? It tells us the amount of change of any parameter let's call that parameter M, in a control system is equal to the amount of change of that parameter with respect to time in a control volume minus the flux of that parameter in and out. So sigma M out from the surfaces. So from the surfaces. This is a general equation. But what does this mean? To understand this, you have to understand what the system is. You have seen this in your thermodynamics and fluid mechanics, right? What is a system? It's a selection in a space which mass doesn't change. That's the idea, right? Meaning that there is no inlet and outlet of that system. What is a control volume, though? Constant mass, control volume. It's a selection space that has a constant volume, exactly. Okay, so based on this, let's see what this principle, Reynolds transport theorem, tells us. Let's go back to that duct. There's one inlet and one outlet. At time 0, I have a mass inside this volume, right inside this duct, and is moving in this direction. What is going to happen to this selection, the red one, at time t1? Moves. So time 0, time t1. So then you want to find out how much of that system is still present in your control volume, meaning that this part of it. What should we do? You have to find out how much of it has moved out, how much of a new system has moved in, and whether there has been any changes inside. Let's say you are, again, think of a combustion scenario. There is fluid flow passing here. Let's say this is a rocket engine, or jet engine. There is air coming in. You have your combustion happening. You're adding fuel, whatever. There is combustion happening. The combustion happening inside is going to make some changes to your air, right? Add energy, whatever, right? But you also have some fluid flow coming in, and some of your system is leaving the whole thing. So the amount of change of anything in your system is going to be equal to the amount of combustion you have, the amount of change within the volume itself. If you have any combustion, if you have electrical current passing through, if you have heating, if you're heating your duct, and the amount of that property that has moved in, and the amount of that property that has moved out of the system. Does this make sense? Okay. Let's try to formulate this using some equations. So using one equation specific. Again, Reynolds transport theorem. changes of a parameter, let's call that parameter in a system, is equals to the changes over time of that parameter. This is system of that parameter in control volume plus the flux, let's call this B dot of that control volume. But how do we calculate the changes inside? The changes inside the control volume, we don't really know whether this parameter B is uniform throughout this duct. What does being uniform throughout the duct mean? It means that we don't really know if this parameter B has the same value here, 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 or here, right? So what we do is we divide it by the mass of the system, right? To find the local value of this parameter B, and then take an integral over the whole volume. I'm just trying to write the equation here. So parameter B dV. Of course, since we have divided it by a mass, I just want to get to it as, again, we are dividing this by a mass. What is mass? Mass is density multiplied by the volume. So eventually I'm going to end up with this type of formulation. And this is the derivative of volume. And then we have to do the same thing for the fluxes. We are dealing with the amounts of that parameter, whether that's velocity, temperature, pressure, that is going out and coming into the system. Mass flow rate, or flow rate of your parameter inside and outside the system. And the equation for that can be calculated using this. This is again density multiplied by your parameter, the rate of moving out or into the system with respect to area. This is the double integral. Triple integral, double integral. This is called the Reynolds transfer theorem. If you don't understand how we got to this equation, that's all right. Don't worry about it. As long as you see the equation, we're going to use this equation and then find our integral form of conservation equations. And there will be one, and this will be the only question on the exam that you will get, a derivation essentially. There will be one question on the exam that will ask you to derive the conservation of mass or moment. Equation, right? You already know the equation, you're doing it right now, just can memorize it, add it to your equation sheet, whatever, and copy it in your exam. But it will be there.
Do you want us to do it in a syllable form or partial form?
Doesn't matter. Integral form is easier because you can start from the Reynolds transfer theorem and just replace the parameter. So Reynolds, what time is it? Because we still have 5 minutes. Let's use this Reynolds transfer theorem for the conservation of mass equation. What did we say? We said this small b, any parameter, it can be any parameter, is essentially your parameter divided by mass. So if this b, the big letter, the capital letter B is your mass, the small b is going to be equal to 1, right? Mass divided by mass is 1. So I'm just going to substitute m for b. Replace b with an m. The total changes of mass of a system with respect to time is equals to the changes of triple integral of density with respect to volume for that system, plus the flux of mass out and in of the system. That is the integral form of conservation of mass equation. See, pretty simple. Yes.
So, on the exam, wants to go from.
We'll talk about the exam later. Focus on learning this. Okay, so essentially, the only thing we did was we replaced this parameter b with mass, right? And then the small parameter b was 1. I just removed it from these integrals. How does mass of a system change with respect to time? What was the definition of a system? Its mass doesn't change. So, based on the definition of a system, in this equation, this part goes to 0. Okay? And then we are going to end up with this equation. So the conservation of mass tells us if you have a change in density for whatever reason in your volume, right here, that change in density will be apparent in your fluxes out and into the system, right? You are going to see that change in density because the mass is neither created or destroyed, right? Well, and we're going to continue the discussion later on, but let's talk about this part. Let's talk about the flux a little bit. Because I just replaced the equation and didn't really explain it. What does this double integral of density multiplied by v times n hat dA mean? Again, I said this is the flux out of the system, right? Or into the system. Let's look at this dot again. Essentially, I want to see how much of this parameter is going out of the system or coming into the system. How can I calculate that? The first thing you want to know is that the flux is always normal to your surface. Okay? So we only care about the movement that is normal to your surface. So if it's moving like this, in this calculation, we have to find the component that is normal to the surface, right? And whenever you hear the word flux, you are talking about the rate of moving out of the system. So it is whatever you have per second, right? Kilograms per second, meters per second, cubic meters per second, right? And the rate can always be characterized with the velocity at that specific location. So the rate of moving out of your system should be related to the normal component of velocity on that surface, that exit or inlet surface, right? How do we calculate the normal component of velocity? And it is always normal component of velocity for the rate of moving out of or into the system for any property. The property itself can be velocity, and we're going to discuss that later. Okay, so how do we calculate this? This n hat is the vector that is normal to it's the normal vector of the surface. It's a surface normal vector. Surface normal. When you multiply the rate of change, I guess, by the surface normal, you are calculating the rate of change or the rate of movement that is normal to your surface or the flux. It's a definition of flux. That's why you see this v dot and hat. So let's just stop here. We're going to come back next lecture. We're going to focus on this and make sure we are all very comfortable with all of these calculations.